Hello everyone. Today in this video we are going to learn about two-port networks. Generally, any network may be represented schematically by a rectangular box like this. Okay? This will be considered as a network. And we already know network is a combination of different circuital elements, right? Now we talk about port. What do you mean by port? Port is a pair of terminals at which a signal may enter or leave a network. That is called port. Let us have a pair of terminals here, okay, at which current is entering and leaving. Okay, right. So this is called a port. And we can even have the voltage across this particular terminals as V. Okay, so how many terminals are there? Pairs of terminals? One pair. So that's why this is called one port network. Similarly, if we have one more pair of terminals at which current is entering and leaving, so this is one more port. Now this network is called two port network, and we can have even have the voltage. Okay, like that you can have the three port networks, you can have four port network, you can have n number of port networks. Okay, so we are now interested in two port networks. Okay, right. In order to have the discrimination between the first port and second port, we are separating them with the numbers. Suffix 1 stands for the first port, 2 stands for the second port. Okay, so before getting into the concept of two-port networks, we need to remember some of the important assumptions there in this particular concept. The first one is that the voltages and currents inside this rectangular box are not available for you. Okay, so that is the first assumption. The voltages and currents which are there inside this rectangular box are not available for you. Okay, and the second assumption is that this network will consist of only linear elements or linear elements along with dependent sources. Okay, strictly there should not be any independent sources. Okay, so this is the second assumption. And the third assumption is that we'll be having inductor and capacitors also. Okay, if we have inductor and capacitors, we have to assume that the initial conditions are zero. Okay, initial conditions will be considered as zero. Okay, so these are the basic assumptions that we need to remember throughout this two-port networks concept. Okay, now one more important point is there. We have I1, I2 there, right? I1, I2. Okay, so the directions of both the currents I1, I2 are assumed to be flowing into the network. Okay, flowing into the network. It is very simple. There is no need to remember anything because here we can consider plus minus voltage polarities. Obviously, the current always leaves from positive terminal. So there is a concept. So if we have minus plus, then obviously you have to take the current direction at a port like this. Okay, so simple. But usually we'll prefer plus to minus. So that's why for a two-port network, so current like this, the direction will be considered. Okay, right. So apart from this point, you have to remember the first three assumptions which are mentioned here. Okay, now coming to the types of networks. Before coming to the types of networks, let me tell you there are four variables there here. As we can see, V1, I1, V2, I2. So these are the four variables, very important variables. So out of these four, okay, so two variables will be considered as dependent variables and two variables will be considered as independent variables. Okay, so in two-port networks concepts, dependent variables will be expressed in terms of independent variables. Okay, so based on this concept, we can have different probabilities. Okay, like V1, V2 can be dependent, I1, I2 can be independent. Like that, we can have different probabilities. So based on different probabilities, we can have types of two-port networks. Okay, so the types may be considered as in terms of you know parameters. Okay, so based on these combinations we can have different two-port network parameters, and are basically first one first one is a Z parameters. So let me tell you dependent and independent variables. So in Z parameters, V1 and V2 will be considered as dependent variables, I1 and I2 as independent variables. Okay, now next one is Y parameters. It's a simple opposite case. So I1 and I2 will be considered as dependent variables, V1 and V2 will be considered as independent variables. And third one is ABCD parameters, or transmission parameters also we can call. Okay, so in this ABCD parameters, V1 and I1 will be considered as dependent, and V2, I2 will be considered as independent variables. And we can even have inverse transmission parameters, but I'm not specifying here. Okay, we'll go with the other type. The fourth one is a H parameters, also called as hybrid parameters. Here in this case, V1 and I2 will be considered as dependent variables, and I1, V2 will be considered as independent variables. And here also we can observe inverse hybrid parameters or G parameters. I'm not talking about those two types, inverse ABCD and inverse hybrid. Okay, so just you can switch over the dependent and independent variables. There you can find the inverse transmission and inverse hybrid parameters. Right, so these are the types of two-port network parameters. Okay, so let us start with Z parameters. Now let us talk about Z parameters. Okay, the first one, Z parameters. These are also called open circuit parameters. Why they were calling as open circuit parameters? Let us see. Okay, so let us consider now a two-port network like this. So this is a two-port network. So we will be definitely have two pairs of terminals. So here I1 and here V1. Similarly, we can have one more port here, V2, I2. So let me tell you, V1, I1 are the port 1 variables, V2, I2 are the port 2 variables. Now, we already discussed there are two sets are there, dependent and independent variables. So in Z parameters, V1 and V2 are dependent variables, I1 and I2 are independent variables. Now we are going to express dependent variables in terms of independent variables. That means V1, V2. These are the dependent variables. So before getting into the equation, we have to remember that V1, V2 are the voltages. So voltage means according to Ohm's law, V equal to Iz is the formula. Okay, so now it can be treated as Z11 I1 plus Z12 I2. Clear? This is first equation. So Z11 is a first port impedance. Okay, so Z12 is a transformed impedance between 1 and 2. Okay, so similarly we can have the other combination Z21 I1. We are writing in a systematic way. So Z22 I2. Okay, so 1 and 2. Now these equations can be expressed in terms of matrix also. Okay, so so v1 v2 as a matrix form like this, and similarly z11 z12 z21 z22. Okay, next I1 I2. So this vector is called V. So this is called Z matrix. This is called vector I or I matrix. Okay, so like this also we can represent. Okay, so here V is called what? Column vector or column matrix, and also current is a column, right? So is also considered as a column vector. And this Z11, Z12, this matrix is there, no? So this is called square matrix or impedance matrix. Now our aim is to find these parameters. So what is the impedance and all we need to calculate. So how we can calculate? Okay, let us consider the case when I2 equal to 0. As we already know, current 0 means it will be open circuited. Okay, so from first equation, V1 equal to what? Z11 I1. That's it, because I2 got 0. So that's why from this equation we may able to calculate Z11 as V1 by I1. So this impedance is called input impedance. So here port 1 is called input port and port 2 is called the output port. Or if you don't like input output, then you can call it as port 1, port 2, no problem. Okay, now go with the second equation. So from second equation, V2 is Z21 I1. That's it. So here we can find Z21 as V2 by I1. Okay, so and we already know that V equal to what? IZ in the case of AC. Now what is Z? V by I. So if you have Z11, keep 1 1. If you have Z12, keep 1 2. If you have 2 1, keep 2 1. So like that you can have the ratio. Okay, right. So here the same thing can be observed. Z11, so it will be V1 by I1. Similarly, Z21, V2 by I1. Okay, so this is the first condition. Now go with the second condition. When I1 0, what happens? Again, it's a current, it will be open circuited. Then from the first equation, what you can get? V1 equal to what? Z12 into I2. So what is Z12? This is V1 by I2. Got it? Now the second equation, from second equation, V2 equal to Z22 into I2. So Z22 equal to V2 by I2. That's it. So we have two different conditions. Okay, so when I2 0, what parameters you are getting? Z11 and Z21. When, sorry, here, right. So when I1 equal to 0, what happened? What parameters that you can get? Z12 and Z. Okay, so in this way we have to calculate the network, and in the same equations can be represented in equivalent circuit form also. Okay, so let me tell you that also. So now I'm rewriting the equations. V1 equal to Z11 I1 plus Z12 I2. Okay, so this is our first equation, and V2 equal to Z21 I1 plus Z22 I2. Okay, so this is our second equation. Now, in order to represent the equivalent circuit, firstly we have to write the terminals at the input port. Okay, so this is V1 input port or first port voltage, and this is the first port current. So here we are not disturbing the port variables. Okay, so first let me draw the port variables as it is. Okay, right. Now look at equation 1. First term, it is Z11 into I1. So, and one more thing, V1, it's a voltage equation. Okay, so V1, V2, all these two equations are voltage equations. That means when you can observe a voltage equation in a loop. So that's why first equation will be considered as a loop equation. Second one is again another loop equation. Okay, so that's why let us consider the first term. So this is our Z11. Now look at the second term. So this second term is dependent on I2. So that's why this product, this voltage will be considered as dependent voltage source like this. This is Z12 I2. Clear? And if you can apply KVL for the first loop, you will be getting equation 1. Okay, so now concentrate on equation 2, this second part. Okay, so first let me write that term. Okay, so this is Z22 and look at the first part. This is again dependent on other port, that is I1, other port current. It is depending on I1. So that's why that part can be treated as a dependent voltage source. Okay, so plus minus, this will be Z21 I1. There should be some link between first port and second port, right? So that can be observed with the reference. Okay, so if you can apply KVL in this loop, you can observe equation. So in this way, the equations, Z parameter equations can be represented in circuit form, equivalent circuit form. And one more thing that we need to remember here, Z11 will be considered as input port driving impedance and Z22 will be called as output port driving impedance. Okay, now Z12 and Z21. So these are called transfer impedances. 1 to 2 will be called as forward transfer impedances and this one is called reverse transfer impedance. Okay, so these are the four impedance variables. Okay, so in this way we can represent the Z parameter equations in circuit form. Okay, this is an equivalent circuit. Now let us go with a problem, right? Now let us solve a problem based on. Okay, so here I am considering a very simple network. Okay, so let us consider a T network. This is 1 ohm, 2 ohm, 3 ohm. Okay, so this is the input port V1, I1 is the input port voltage and here V2, I2 are the output port voltage. The Z parameters. Okay, so what we need to do, we have to write the Z parameter equations. We already discussed V1 equal to Z11 I1. Okay. Z11 I1 plus Z12 I2. So this is our first equation. Now V2 is Z21 I1 plus Z22 I2. Okay, so this is the second equation. Now we apply the conditions. Now first what we apply, when I2 equal to 0, what happens? Open circuit will be happening. Under this condition from equation 1, what parameter that you can get? Z11, that is V1 by I1. Similarly from second equation we can get Z21 as V2 by I1. Okay, so now let us draw the network under this condition. Okay, now without anything, first write the skeleton. Okay, right, so this is 1 ohm, 2 ohm, 3 ohm. Now what is the condition? I2 0, so that means the second port got the open circuit. Now that's why this first port will be considered as supply voltage, this current as supply current. So I2 0 means it does not mean like V2 is 0. Okay, so V2 will be there. It will be considered as measured voltage. So V1 is supply. Since So there is no need to do any kind of calculations. You need to calculate I1 and V2. That's it. Okay. Now, as you can see, the current I1 circulates here like this. So shall we find I1 now? So I1 equal to V1 by what? Resistance 1 plus 3. So this is V1 by 4. This is the first equation. Now we need to calculate what? V2. So let us have the polarities plus minus here. So here also plus minus. Now concentrate on V2 side. So from plus to minus, in order to reach plus to minus, which is the simplest path? 2 and 3. So that's why voltage across 2 ohm resistor plus voltage across 3 ohm resistor you need to consider. Now since the current I1 is flowing like this, so here is plus, here is minus. Okay. Now is there any current flow in 2 ohm resistor? No. So that's why voltage drop is 0. So now current flowing through 3 ohm is I1. So 3I1 is the voltage drop across 3 ohm resistor. Done. So V2 will be 3I1. So this is our second equation. Now start solving the parameters. Z11 equal to what? V1. Don't write anything for V1 because it is a supply voltage. So V1 by I1. So what is I1? V1 by 4. Obviously you'll be getting 4 ohms. Now go for the other one. This is Z21. This is V2 by I2. So V2, what is V2? What is V2? V2 is, from equation 2 we can say, that is 3I1 by, don't write any substitute for I1 because it is straight away cancelling. Okay, it will be 3 ohms. That's it. So first case is over. Now go for the second case. The second case is when I1 equal to 0. Again, what condition can be observed? Open circuit. So from first equation, what parameter can be obtained? Z12. Z12 equal to V1 by I2. Okay. Now from second equation, what parameter can be observed? Z2. That is V2 by I2. Let us redraw the network without any late. So this is a skeleton. This is 1 ohm, 2 ohm, 3 ohm. Now I1 0, that means first port got the open circuit. So now the second port will be considered as supply voltage, and here is a supply current, and here V1 will be considered as a measured voltage. Okay, so let me erase it and clearly I'll write. Okay, so this is measured voltage V1. Okay, now this I2 is circulating like this. So this is plus, this is minus. Now what is I2? I2 is what? V2 by resistance 2 plus 3. So this is V2 by 5. Okay, call it as equation 3. Now it is the time to calculate V1. So why we are calculating I2 and V1? Because with those parameters, with those values only we can find the parameters. And why we are not calculating V2? So here V2 will be considered as our supply voltage. So that's why no need to do any kind of calculation to find V2. Okay, so now V1. So let me write the polarities plus minus. Okay, so how can you reach V1 plus to minus? Simplest path, voltage across 1 ohm plus voltage across 3 ohm. That's it. No current flow through 1 ohm, so voltage drop is 0. So voltage across 3, that is 3I2. Okay, so now what we can write? V1 equal to 3I2. That's it. You got the fourth equation. Now go for the parameters. Start this one. Okay, what we can find? Z12 equal to what? V1 by I2. So V1 is what? 3I2 by I2. So I2 gets cancelled, you'll be getting 3 ohms. Now go for the second parameter under this condition, that is Z22. So Z22 equal to what? V2 by I2, right? So what is V2? It's a supply, no need to write anything. Now what is I2? From equation 3, what we can write? V2 by 5. So this is 5 ohms. So did you find any pattern in these parameters? Yes. So you can observe this Z21 equal to Z12, which is of same value. You can observe. Whenever you observe the condition like this, the network will be considered as a reciprocal network. Okay, so let me tell you the impedances, what we call those impedances as what is Z11 and all. So here Z11 is called as driving point impedance. Okay, driving point impedance. Z22 will be called as output driving point impedance. Okay, so whereas Z11 you may also call as input. Okay, input driving point impedance. Okay, now Z12 is called 12. It's a forward. Okay, so that's why it is called forward transfer impedance. Z21, so output to input. So that's why it is called reverse transfer impedance. So this is about Z parameters. In coming videos, we'll be discussing Y parameters and rest of the parameters, their interrelations. Okay, so every topic will be covered. Okay, so I hope this video will help you in doing a calculation like Z parameters. Okay, so thank you so much for watching this video. See you in the next video. Thank you.